Assalamualaikum warahmatullahi wabarakatuh. Good evening, ladies and gentlemen. Welcome to Guest Lecture with the title Analysis of Fractional Factorial Design. My name is Zuria Hima Pratuain, and it's a honor for me to be a master of ceremony on our Guest Lecture today. It's a pleasure to meet all of you. First, please welcome to our honorable guest, Dr. Anthony Ekbu from Department of Statistics, College of Physical Science, Yosat Sarwan Tarka University, Makurdi, Nigeria, as our speaker today. And welcome to our Dr. Nur Hamidah, MSc from Statistics Study Program, Faculty of Science and Technology, Universitas Airlangga. Also welcome to all the amazing participants from Indonesia and Nigeria. I'm delighted to welcome all of you to this special guest lecture today. We have the privilege of hosting a distinguished expert in the field who will be sharing invaluable insight into analysis of fractional factorial design. Before we begin today's enlightening session, let us take a moment to offer a prayer, seeking guidance and wisdom for our session. Pray based on our belief. Begin. Amin. Now we would like to invite you to sing along to the Indonesian anthem, Indonesia Raya, and Universitas Airlangga Hymne. For the commit in chat, you might share your screen. Okay, thank you for your participation in singing along. Dear all participants, now let's create a memorable snapshot for our time together. Even though we are not the same physical space, we can still capture this moment in a virtual photo. Please turn on your camera and I will wait for a minute. Okay, because all the participants are ready, on the count of three, let's all strike a pose and give our space smile. 1, 2, 3. Okay, move to the second slide. 1, 2, 3. Thank you. We encourage all the participants not to turn off your camera. This not only allow us to better connect, but also help create a more dynamic and engaging environment. Okay, it's now time to transition into the heart of today's event, the keynote speaker session. We are about to embark on a journey of knowledge and insight. To with us start this enlightening session, I have the pleasure of introducing our esteemed moderator, Kezia Unica. Please join me in welcoming Kezia, who will with us start this lecture session. For Kezia, the virtual stage is yours.
Thank you very much for the introduction, Hilma. Good evening to our Indonesian participants. Good afternoon to Nigerian participants. Greetings, everyone. Good afternoon, Dr. Anthony. How are you today?
Fine, good afternoon, and you?
Really nice to hear that. I'm also really in a great place right now. Last week, we learned about factorial design, confounded factorial design to be specific. And in today's lecture, we are going to learn about analysis of fractional factorial design. And we will be taught by Dr. Anthony Ekpo from Joseph Sarwantarka University, Makurdi, Nigeria. Like the previous sessions, we will have about 90 minutes for the lecture session. And with that, it will be followed with a Q&A session for about 15 minutes. But before listening to our lecture today, allow me to introduce you to Dr. Anthony through his CV. And I will share my screen. Please tell me when it's already shared, okay? Can you see my screen, everyone?
Yes.
Okay, so let me introduce you to our speaker of the day, Dr. Anthony. Dr. Anthony is currently working in Department of Statistics, Federal University of Agriculture, or also known as Joseph Sarwantarka University in Makurdi, Benue, Nigeria. He is a very intelligent person, as you can see from his track record as well. He has undergone many educations, some of which are bachelor's in statistics in University of Uyo, and then master of statistics, especially in experimental design, which is what we're going to learn today, in University of Nigeria, and then another master of statistics in biostatistics in University of Ilorin, and a PhD in statistics as well in Joseph Sarwantarka University. And he also has a lot of skills, which includes training courses. As you can see, the courses that he has already gone through, and he also received fellowships and scholarships from many institutions. As you can see, it's a very credible institution as well, which includes UNICEF is one of them. And then he also has computing skills in many of us softwares that we might know, like Microsoft or SPSS and other softwares. He also has a lot of experiences both in teaching and also in statistical consultancy. And he also has a lot of publications. And with all the experiences that you really need to know that he is credible for this session, and we will definitely learn a lot from him. As you can see, he also has conference papers and webinars and many more experiences. So without further ado, let's welcome our very honored speaker of the day, Dr. Anthony Ekpo. Doctor, the time and screen is yours.
Thank you very much, Casey, for that wonderful introduction. I want to thank everyone for finding time to be here. Most especially, I want to thank the students who, in spite of the time schedule, have also found time to be here. My students in Nigeria who can also be here, I welcome you. I also want to thank very especially my supervisor, Dr. Nur Chamida,
Hello.
for this wonderful work you are doing.
Okay,
Yes, I'm glad
thank
to be
you.
here again today. So I want to thank all of you who have found time to be here, and I want to believe that your time here will not be a waste. Within the next couple of minutes, we'll see what we can do in this subject for today. Without wasting much time, let me share my screen. Please, once you see the screen on, just let me know. Okay. So that is the screen I'm going to use. And then incidentally, we're starting from the beginning. Can you see my screen, please?
Yes,
Yes,
it's
please.
If you
clear.
can see my screen, can you just wave your hands? Good, good. All right, thank you. Thank you so very much. Just like you know, this is the third series in the series of lectures we've been having on factorial design. Now, you are aware that when we started, we were thinking we're going to end with just 2 sessions. But incidentally, the topic is so broad that we needed to expand it into 3 sessions so that the students will be able to follow. Now, most especially because some of the students that are in participation here are not basically statistics students. So we will try to make it slow and easy for them to follow us.
Okay.
So today's session happens to be the last in the series for factorial designs, except maybe we'll look at other topics. But what we have here is narrowed down to up to year 3, year 4, so that at the undergraduate level, you'll be able to get insight into what Department of Statistics, Joseph Sawantaka University here in Nigeria. So, in this particular session of the lecture, we're going to we'll try our best so that at the end of this lecture, students should be able to do the following and understand the following. First of all, the students should be able to, at the end of this particular lecture, I'm sure that students will be able to understand the application of fractional factorial design. Because if you had attended the first and the second sessions, you would have noticed that we have done part of confounding, and then we have introduced the factorial designs. But in this particular session, students should be able to understand how to apply the fractional factorial design. Then students should also be able to become familiar with particular terminologies we're going to be using. One of them is the design generator. Then we're also going to be talking about alias structures. I'm also going to be talking about design resolution. So in this particular lecture, I expect students to be familiar with these 4 terms, or rather these 3 terms. Then students too should be able to know the key principles of a successful use of fractional factorial design. So by the time you use fractional factorial design, you should know whether you have successfully used it or not after these lectures. Then students also should be able to know the aims and utility of the fractional design. when do you utilize it? Students should be able to know when to use it. The students should also be able to know, and then those drawbacks, particularly disadvantages of using the fractional factorial design. And at the end of the day, students should also be able to know how to analyze fractional factorial design. So these are the key areas where we are thinking that students should be able to follow. So we also will start with definitions, because usually it is important that we define the concepts so that we're able to flow together. Now, when the number of factors becomes too large than what you expect in your design, most especially when you are dealing with the factorial design of 2 power k treatments, now it becomes very unnecessary or impracticable to carry out the 2 to power k design, particularly when the factors becomes too large, more than what you can expect. So rather, a fractional factorial design becomes necessary as the option here. Now, because it provides an alternative means of concentrating experimental investigation on only those treatments or those treatment combinations that are of interest. Now, what happens usually is that if you have a large number of factors, you may lose track of which ones are important. And that's why it is important to fractionalize them and see those ones that are important. And then you don't just choose those ones that are important on your own. You need to follow through the process of the fractional factorial design to be able to do that. Okay? Now, consider a situation in which 3 factors, all of them at 2 levels, are of interest. Here you're talking about a 2 to the power 3 factorial design, which of course is going to yield up to 8 runs. Now, but the experimenter has no means to conduct this experiment, and he only has maybe the means for 4 treatments instead of 8, or 4 runs instead of 8. So what he does now is to consider the fractional factorial design. And that's why you see we have 1/2 times 2 to the power of 3 fractional. So it is this 1/2 that makes the design fractional, as the name implies. So here now, instead of using 8 runs or 8 treatments, you have reduced that 8 to half of them. And by that doing, you will save time, you will save costs, and also save manpower. So this is why we suggest that when your factors become too large, you go to do the fractional factorial. And this will not make you lose information at all in the process. Now look at this now. Consider in this illustration, we're going to consider the yield that contains the even number of letters. You remember in the 2 series we have had, we have talked about the yield, where we've been giving you these treatment combinations and then these factors here. So for those that are new to the class, what you have here on the horizontal axis are the factors. And what you have here on the vertical axis are the treatment combinations, which are levels in the factors. So here, in an attempt to dwell on a fractional factorial design, you are going to be using the even and odd option as the elementary way to select. So in the even option, what you will do is to concentrate on your yield that are even numbers. When I say even numbers, I mean like 2, 4, and so on. So among the treatment combinations that you have here are these even numbers, even letters AB, AC, and BC. Of course, you know that this one in open and close bracket is the low level of all the factors. So here, our interest is to take 4 treatments as against 8 treatments. So that's why we have divided into 2 the entire sign table into 2 equal parts. Here we are dwelling on the even numbers or even letters. So 1, 2, 1, 2. That makes it even. So what we do here is that we want to see how we can form a block using only the even letters. So you can see this color here. This is color blue. Now we are looking for a combination that will give us ABC. ABC is the interacting factor for all of the factors. Okay, so we want to see how we can form a block of 4 treatments using ABC as the interacting factor. Okay, so now you can see under the blue, you see A here. A is minus, multiplied by BC, positive, that will give you minus. It means A minus times BC plus is minus. So ABC is now minus. I hope we're following. A times BC is ABC. And if you look at the sign under A is minus, the sign under BC is plus. So when you multiply minus under A and plus under BC, you have a minus. All right, and that minus signifies block 1 because it is negative, as we'll see later. Now, if you go to, that is for A and BC. If you go to B, in fact, if you do the same for AB under A, you have positive plus under A multiplied by BC minus. That will still give you minus. All right, so you use these minus signs to form the first block where you have fractionalized your 8 treatments into half. Okay, so the same thing happens under the yield AC. For A, you have minus, and then for BC, you have, for A you have plus, for BC you have minus. So this plus under A multiplied by minus under BC is minus for ABC. So you see, we have gotten all minuses for A and BC because here we're considering our generator ABC. Okay, so now when you go to the B, you are combining B and AC because when you multiply B and AC, it gives you ABC. All right, so under B, your first yield here, which is a low level of all of the factors, is minus under B. And then you also have under BC, you have B minus multiplied by AC plus, that will also give you minus under ABC. It's very simple. So you do the same for AB. Under the interaction or the combined treatment AB, for B, you have you have plus. And then for BC, under AC, you have minus. So plus multiplied by minus gives you minus. You can see under ABC, you also have minus. So you see the same thing happens for these same colors. Plus multiply minus is minus. If you come to B, minus multiplied plus is minus. So with these signs and with these even numbers here, we have been able to form a block of the even numbers, thereby excluding the odd numbers, odd letters, and then you have formed a fractional block of 4. So you can use the even number of letters as treatment combinations to form your block. That's the first thing. Now, if you take a look at the first block, which is half fraction of the full design, with ABC as the generator, you'll notice that you have shared the block into 2. So now the block you will be interested in now is the block yielding 1 open and close bracket, low level of all of them. The next combination is AB, the next combination is AC, and then followed by BC. So in this particular case, you are talking about ABC at -1. That's what we mean here. ABC now is at -1 within the table. So under ABC, you have it at minus. All right, let's go to the next table. Now let's go to the next table. Now you notice that under this illustration 1, the defining contrasts, which is combined with those colors you see there, are at minus. And that's why you see, by implication, the I here, which is the the main effect is going to be minus ABC, and A is going to be minus B, B is going to be minus AC, where these values of interaction are their aliases, as we will see later in the main definition. Now, this goes on and on like that for the even number of letters. Let's look at what happens for the odd number of letters. Now, for the odd number of letters here, we have A, level of A, level of B, and level of C, and then ABC. You can see that the level ABC is 3 letters, and that makes it odd. The level of A, B, and C are single letters 1, 1, 1. That makes them odd. So using the odd format, you can also form the second block with ABC as your generator, thereby making your fraction of that 2 to the power 3 design into 2. So you can see here now, under the yield A, level A, the factor is positive, okay? And then for you to combine A, you must combine with BC to get your ABC. So when you multiply the run in A, which is plus, multiply by the plus in BC, you have plus. I hope you're following. That gives you C, and then the plus multiplied by plus. Now you can see that with that, you have formed a table where you have been able to share the table into 2. Now, if you do the same for the yield B, this B is a treatment combination. Under B here, for this color, you have under A, you have minus, and under BC, you have minus. So minus multiplied by minus gave us plus. You can see that. So you are generating the signs plus under ABC, so that it will enable you have a block, which you call block 2. And this block 2 will be formed by only the odd letters, as you can see here. Remember, the former one was even letters. Here you have the odd letters. Odd as in A, 1, B, 1, C, 1, and ABC, 3. These are odd letters. So the odd letters now have formed the second half of your block, which has made it a fractional factorial design. So you have shifted the fractional design into a fractional factorial design. So that's how it's done. If you look at the BC now, ABC now, they are populated with the signs plus, meaning that our block here is that of positive. Okay, so if you verify that, your I will be equal to ABC, positive, your A will be equal to BC, all right? Your B will be equal to AC, and your C will be equal to AB, all of them positive, unlike in the other case. So with this now, you've been able to fractionalize the 8 will have been treatments into 4, and then you use the 4 for your analysis, and that means you have concentrated with half of the entire 8, and that makes it a fractional factorial design. Now let's look at some of these definitions. I've used the word aliases, alias structure. Now when we talk about the aliases, there are also effects, okay? There are effects that you have when you try to partition a main effect and an interacting effect. For example, if you have a defining contrast multiplied by the effect, it gives you the alias. Alias means the half or the fraction of the effect you have selected. Now, when I take my I, which is the main effect, the I is equal to ABC. If I take my A is equal to BC, because the BC is the remnant if you remove A from ABC. The same thing happens with B. If I take off B from ABC, what is left is AC. And then this AC is called the alias of B. And B is the alias of AC. Okay? So we need these alias structures in the fractional factorial design. They are like confounding, they are like blocking. But we call them aliases because they are alias to each other. So a main effect is alias to an interacting effect of two factors. So C is alias with AB because out of ABC, if I remove C, what is left is AB. So AB is aliased with C and C is aliased with AB. Try to get that. So I is aliased with ABC, where I is the main effect, okay? Is the main effect because it's at the level of all of the factors, okay? So when I multiply that I by ABC, it is still ABC, okay? The same thing happens, A is aliased with BC. If you multiply A and BC, it gives you ABC, and so on and so forth. So this is important for you to take note of. So we also have what we call the design resolutions. Now, these design resolutions are what the highest interaction generates. Here we're dealing with 2 to the power 3 factorial design. That means there are 3 factors. So because 3 factors are involved, that means we are dealing with resolution 3. And it's written normally in the Roman numbers. Okay, so when we talk about a resolution, we're talking about the highest level that a fractional factorial design contains. We are dealing with 2 to the power 3, and that means that our factor here is 3. Our factor here is 3. Now, when we write it in this form, a 1 over 2 multiplied by 2 to the power 3 is the same thing as saying 2 to the power 3 minus 1 fractional factorial design, and it is called a resolution.
There seems to be a technical problem, so we will wait a little bit until Dr. Anthony gains his signal back.
Create design. Is that okay? You can see we have written 2 to if it has a replicate. So in this particular case, the replicate is 1.
Whoops, apparently.
Lempar.
Yeah, there has been a technical problem, so would you please wait for a little bit?
Di sini ada yang dari anu loh. Tadi saya lihat namanya apa tadi? Rafael. Hello, Rafael. Kesia, could you say hello to Rafael?
Yes. Yes, there are actually many attendants that are from Nigeria. Hello, Mr. Rafael Ekpo, and then hello, many others. Okay, Dr. Anthony is back.
Okay.
Can you hear me now?
Yes, we can hear you, but
sorry,
we cannot
network.
see you.
Can you see me now?
Yeah.
Not yet. We cannot see
Oh, no,
you.
no, not yet. Not yet.
We can hear you, but we cannot see you yet.
You can't see me yet.
Yes.
I'm sharing my screen here.
Okay.
Okay.
Yeah, we can
Can you
see
see me now?
Yes, we can see
Yes.
you on your screen.
Sorry about that. Sorry about that. Network can be problematic at times.
Yes.
So I'm sure you are seeing me now, and you are seeing the slides too.
Yes, we can see
Kezia,
your slide
can
as
you
well.
wave?
Yeah.
You're seeing me? Okay, fine. All right. So the 3 kinds of resolutions that we are going to be discussing. Here we have resolution 3. I've mentioned that before. We also have resolution 4, and then we also have resolution 5. These are the major resolutions that we're going to be looking at. When we talk about resolution 3, we are looking at resolutions A, C. If we're talking about resolution 4, we're talking about 4 factors, A, B, C, and D. A, B, C, and D. Okay. In each of these, the interesting thing is that for the ABC factors, like you saw before, the main effect, whereas for the 4-factor interactions, you find out that no main effect is layers with other main effects. Rather, the 2-factor effects are layers with another 2-factor effect. For example, AB can be equal to CD. Okay, so 2 effects can be layers with another 2 effects. Now, but for the resolution 5 designs, here you do not find any main effects or any other factor interactions in a layers with any other main factor. Okay, so here you usually will find 2-factor interaction aliasing with 3-factor interaction. For example, AB can be in alias with C, D, and E. Okay, so a lot of these things you will look at. We may not be able to exhaust all of them here, but these are the principles you need to follow. Now, for you to successfully use the fractional factorial design, you must be very conscious of these following principles, which we call the basic principles. Now, the first one is the principle that of the sparsity of effects. Here, you are looking at the possibility that several variables or treatments in the experimental process are likely to be driven by certain main effects. Okay, so you may be interested in certain main effects and even some low order effects. It can be majorly 2-factor effects. So it might not be exactly the one you are interested in that becomes the factor that do not contribute to the experiment. So there's this sparsity of effect, which you must be very careful about. It can shift from what you expect to what you do not expect. There's also the principle of projection. Okay, in this principle here, you must be conscious that your factorials, when you have fractionalized them, there are strong tendencies for some of them to be able to form subset of significant factors. It can either be small or in large numbers. You can have AC and maybe BC becoming projections to each other in that form. So it's important to also take note of that, so that you don't remove 2 interacting factors that are in projection to the other. So these principles have to be looked at. Then useful of sequential experimentation principles. Here, you can combine runs that are of different fractional assembly into different sequences. That is to say, you can use AB, you can use CD, and then put them into a sequence so that the interactions become a combined interaction that you deal with in sequence. So these are 3 very important principles that you must always be careful about when you're dealing with the fractional factorials. Now, in using the fractional factorials, you must also be sure that you know exactly when to use them. For example, a fractional factorial design is mostly used for product and process design, okay? Or when you want to improve on the process or the capability of a process, because it usually is good when it comes to screening of your effects. Okay, you want to remove some effects. So what you can do is to employ the use of the fractional factorial design. Then you also have to use this, especially when you are involved in screening experiments, because some factors may not be important like others. And for you to eliminate a factor, you don't just eliminate it without checking. So fractional factorial design helps you to eliminate a factor which does not have any significance in your experiment. Okay, and then again, the fractional factorial design helps you to reduce the size of your experimental materials. Most especially, it helps you to reduce cost of manpower and also helps you to reduce time, because instead of using 8 factors, and then you're able to eliminate 4. It will save you time and cost in the other 4, and without losing information from the 4 you will use. So it's important also to know that. And then it enables the experimenter to focus his interest on those effects that are of interest, while sacrifice information on the effects that are of less importance. So you will concentrate giving out the order, like we did in the first example I gave you, the first illustration, where we use the even letters. We have eliminated the other 4 that are odd. So by so doing, you are focusing on the odd or on the even. Now, there are some disadvantages of using the fractional factorial design. Just like we talked about earlier, the aliases, when you eliminate them, can bring in bias. For example, if I'm using factor A and BC, and at the end of the day, I'm using BC as an alliance for A, or as a completeness for A, you can see that the main effect that A will have brought will not be there. So there could be some bias in that particular experiment. But then the important thing is that the interaction effect can come in and be better than the main effect. Now, some effects cannot also be estimated at all. There are some effects you cannot estimate. And that's why if you look at some of the ANOVA tables you'll be generating, you will not be having responses for the residuals, because those particular effects will have been removed from the onset. So this means that one cannot form a linear contrast. And once you don't form a linear contrast, you will not be able to find all the interactions A, B, and C contributing in the estimates. So there will be some unbiasedness coming in. Now, in general, too, the treatments which are used, particularly when you split a 2 to power k into 2 that are called the dividing contrast, you will not be able to estimate them in the experimental process. So once you remove or eliminate any factor, because you have brought in fractional factorial, that means you may not be able to estimate all of those factors, and then your defining contrast will not be complete. And once it is not complete, some unbiased will have set in. So let's take this particular design as our example. This is half of a 2 to the power 4 fractional factorial design. Here you see typically we're dealing with a resolution design of factor 4. Okay, level 2. It is 2 levels, it is 4, and it is of resolution 4. Why is it resolution 4? Because we're dealing with focus A, B, C, and D. Okay, all of them have 2 levels. We have mentioned that in our first and second session. Now, this particular design originally should yield 16 runs. When I say 16